Electromagnets. What are they? How do they work? Why are they useful? Some of these questions and more answered in this video. I want to experiment with making custom electromagnets, or magnets that are powered by electricity. Electromagnets are the basics of all movement in robotics, as motors are just electromagnets that are turned on and off at the right moment to create torque in a motor. Creating custom tiny electromagnets should allow me to make smaller functions in an animatronic where high torque or precision isn't required. This actually has a huge history in animatronics because the original animatronics, the Tiki Birds at Disneyland, their mouths were actually just electromagnets directly connected to the sound wave, so its mouth opened when there was sound coming out of that bird. So how are electromagnets actually made? It's much simpler than you would expect. It's just actually a coil of wire. Specifically, this kind of wire. This is called magnet wire, and it's called magnet wire because you make magnets out of it. Who would have thought? So it's super, super thin. You can barely see it there. It's super, super thin and has a super thin coating of enamel on it as an insulator. This wire specifically is gauge 36, which means it's 0.15 millimeters in diameter, so super duper tiny. And why is this tinyness a good thing? Well, that allows more windings. And why it's more windings a good thing, I don't know. That's what we're trying to figure out in this video. So to test electromagnets, I've printed out these super small little pulleys to wind the magnets on. They are 8 millimeters in diameter by 5 millimeters high. And in order to wind them, I'm going to use this electric drill and this little 3D printed tool. The pulley screws on the front side, and then this gets put in the chuck. And it has this arm here, so I can see every revolution and count it. And then the magnet wire is on this wooden peg that's attached to the table via this vise, so it can spin as the electromagnets are coiled. Alright, I have the little tool in the chuck with the arm up top, and then the pulley is screwed to that with an M through screw that just goes straight through. And then we take the magnet wire, we put it in the little groove that's on the pulley, we start spinning it so that it catches. Then we just count. For this first pulley, I'm going to do 50 turns. 6, 7, 8, 9, 10, 11. Alright, so I have 50 turns on there. So next up, I'm just going to apply a little bit of super glue to make sure it stays there. Just a dab of super glue. And then we can cut the other end here and unscrew it. So in these experiments, I want to test the current draw of all the different numbers of turns and the strength. So for the current draw, what I have here is a computer power supply, and I'm taking a 5-volt rail from it, and then I'm running the power through this multimeter in amperage mode, so it's measuring the amps that go through it. Then I'm connecting this electromagnet to it and measuring how many amps it draws. So what I'm going to do is strip the ends of this, and you strip ends of cable like this just with some sandpaper, just to get the thin layer of enamel off. You also have to be very careful while doing this so you don't rip the cable. It's very, very thin. So we take the 5-volt rail and we connect one side of the electromagnet to the 5-volt and one side to the ground. Just making sure I get it aligned correctly. And we see it draws just about 1.3 amps. And I disconnect that very quickly because I happen to know something about a low turn coil like this. which is it really likes to get really hot. And the thing about really hot things and plastic like this is it melts, which this electromagnet here did actually melt, and that's why the plastic is all deformed. So I'm not going to leave this one plugged in for too much longer, but I'm going to take note that it drew 1.3 amps. All right, so let's look at how we're going to measure the strength since we already measured the amperage. For the strength, you can't just directly put it on a scale. Now, there are meters that measure electricity or electromagnetism, and those would be Tesla meters or Gauss meters. I don't have either of those, so we're going to do it in a more janky way. My more janky way includes a lever made out of a paint stick with one side resting on a scale. Now the scale is tarred, which means it's zeroed out, and I have a magnet taped to this. So on another magnet, for reference, I'm going to use one of these refrigerator magnets. If I put it underneath it, it sucks right up because it is very powerful. But you can see it pulls on it 34 grams. Now this doesn't give us an absolute measurement like a Tesla or Gauss meter would, but it gives us a relative measurement. So if we know this pulls on it with 32 grams of force, then another magnet is relative to that, which is all we really need. Now for reference 2, I have a little neodymium magnet. This is the same size as the electromagnets we'll be winding, and it pulls from the same distance as the kitchen magnet with a force of 3 grams. Because the electromagnets are going to be quite small, I'm actually going to use this bigger stand, which was too tall to use with the kitchen magnets. But with the neodymium and electromagnets, it should be about the right height. And you see it's pulling with 15 grams of force now. Now look at the electromagnet setup. I have it taped to the box down here, and the scale is tarred, so it's zeroed out. And then if I connect these coils to the jumper cables here, that was fun. You can see it in that last clip, but what happened is the electromagnet was on, but I couldn't tell by the scale reading, so I left it connected. And because it draws so much amperage, it actually got hot enough to start melting the plastic, and it starts smoking, which isn't the best for anything. Looking like this setup isn't actually sensitive enough to detect this electromagnet. And I'm not sure if that's going to change with more winding, because once again, this is the point of the video. But I'm going to have to find something more sensitive, and that might mean moving the magnet back for more leverage. Alright, so after the last fail with the electronic scale, I tried this mechanical scale too, and this also just isn't, the magnets just aren't strong enough to actuate this in a meaningful way. So I think we're going to have to change the idea of finding the strongest number of turns to the one that has the least amount of turns that doesn't smoke. That'll be the plan. So for reference, I always knew that the strength of an electromagnet is actually tied to the amperage it draws, because amperage is derived, you multiply volts times your amperage to get watts, and watts is your power. And the strength of an electromagnet is tied to the power that you feed it. So I really just wanted to use the scales because it'd be a lot easier to visualize, but we know that the more amperage it draws, the stronger the electromagnet, but the more it heats up too. Alright, so I'm going to take these 7 other little pins I have, and I'm going to wind them in every 25 turns. So for this one I'll do 75, then 100, 125, 150, until I can no longer fit anymore. Then we'll go back and test which one will be ideal for making our own electromagnets. Alright, so I have all the electromagnets wound, and all that we need to do now is check how much current each number of turns draws, and whether it starts melting the plastic. So, first up is the 75 turn electromagnet. Alright, 70 turns draws just under an amp. Let's see if it starts smoking. No smoke yet. Oh, there it is. I don't know if you can see that in the video, but that was it smoking. And that is it very hot. Alright. Smells now too. Next up we have the 100 turn electromagnet. Alright, 100 turn, looks like it's drawing 0.83 amps. No smoke yet. The amperage seems to be dropping as time goes on. Not sure what that means. And that's definitely it doing something not good. That is hot. Okay. Next up we have 125 turns. Alright, 125 turns seems to be drawing 0.73 amps at 5 volts. Is it going to keep going? Keeps dropping. Yep, that is smoke. Cool. This feels safe. Yeah. Alright, next up is 150 turn. 0.700 amps. You get stuck to the table. No smoke yet. There it is. Ooh. That's not a good one. Alright. Maybe 175 turns will be the correct amount, so that it doesn't melt itself. About 0.6 ohms. 0.6 amps. So 175 turns looks to be drawing about somewhere between 0.5, 0.6 amps. Let's see if this one smokes too. It's starting to smell pretty bad. It should start smoking real soon. I'm going to call that. It looks pretty melted. There's a poker. Oh, that's super soft. Look at that. That got really soft. Alright, one last test at 200 turns. 200 turns is drawing about half an amp. Alright, it's starting to smell like burning. Temperature term seems to be fine. It hasn't started smoking yet. Let's see how soft it got. That's still really soft. See, I could jam right into it. Where's the camera? There's the camera. See if it will focus. Well, anyways, it got really soft, and that is really hot. Okay, yeah. So in conclusion, it looks like no matter what we do, it's always going to melt the plastic, and that's just because there's upwards of 7 watts in some of these designs that has to be dissipated just through plastic, and this plastic is not a good thermal conductor. In fact, it's designed to melt so it can be 3D printed. So of course it's going to melt as that temperature rises. So we're either going to need to put it on some active cooling place, like have a fan blow over it, or just put it in a place where it doesn't matter if it gets really hot. So you might be wondering why I'm playing with these tiny electromagnets. And that is because I'm designing an animatronic eye that is driven from the inside. So electromagnets go inside the eye instead of having 2 servos behind. I'm hoping that will reduce loudness so it'll be quieter and it'll move smoother and faster. So ideally, that will make a better eye. So make sure to check that in the future. But until then, make sure to subscribe, hit the bell icon, and hit the like button if you like this video.